Okay, coming back in and taking a look at what we've done before and kind of what we're doing now. So we talked about the degree of the denominator being larger, having a horizontal asymptote of y equal to 0. Kind of the point for this one is that the degree of the denominator is larger than the degree of the numerator. Oops, sorry, the degree of the denominator is smaller than the degree of the numerator. Then there will be no horizontal asymptote. If I kind of make that connection to the limits, kind of like what you're going to do in calculus, if I was going to do the limit as x, again, I'm just looking at the right-hand behavior, as x goes to infinity of the numerator divided by the denominator as functions of x, that we do the same kind of idea since you're doing end behavior. We do this survival of the fittest, the fastest, kind of a Darwin-esque type scenario. So for this first one, so g of x, the winner in the top is going to be x squared. So limit as n goes to infinity, we choose the x squared. I'm going to do the second one. So that would be the bottom. The winner would be 2x. And then when we simplify this, the limit as x goes to infinity, that's an x right there, you would have 1/2 x. Now, what's right there is what's controlling the ends of the graph. That's what we call the ratio of dominating terms. And if you think about as x goes to infinity, what is 1/2 times x going to do? It's also going to go to infinity. So you can see that the end of the graph is going up and heading to infinity. That's there. This is also true. I mean, even if you had something that was a degree like cubic or something. So if I had and I'll let you guys take a look at this graph in Desmos, if g of x was x cubed minus 5x plus 6x minus 3 over 2x plus 4, you will see that it will have the same behavior. Same kind of concept. If I look at the limit as x goes to infinity, the winner in the top is x cubed. The winner in the bottom is 2x. Although I guess technically I should label this kind of the notation of limits. Whoops. We should do of g of x, and then we're doing the end behavior as x goes to infinity. That g of x follows the dominating terms, x cubed over x. I simplify. That's going to give me 1/2 x squared, and then you could ask yourself that question in your head. Sorry, I keep forgetting to always do that to slide over. So I did the limit of g of x. Where's the end of g of x going? The right end, because it's going to infinity. I chose the two dominating terms, x cubed and 2x. I simplified. I got 1/2 x squared. I asked myself where it's going. Of course, that's going to infinity as well. So we can get that idea of the end behavior fairly easily from that. You don't actually have to write the calculus and the limit notation down, but understanding why it works and where you're going is kind of important. Now this one, it might be interesting to go ahead and show you the left end behavior of that same one, because when we're looking at that one, something a little different happens. So I'm just going to add it down here. The limit as x goes to negative infinity. So as you go to infinity, that's the right. As you go to negative infinity, that's the left. So we take that numerator over that denominator. And again, I'm just going to start going back to, let's just, because we really don't separate it out that much. A lot of times we just say g of x, and then we pick the winner in the top and the winner in the bottom. So it's x squared over 2x. That doesn't change. It's still going to be 1/2 x. But in that one, when you ask yourself, what's the left end behavior of a line with a positive slope? That line is going to go down to negative infinity. All right, so, and then we'll come back and we'll talk a little bit more about what type of asymptote this is. This is an example of a slant asymptote because it's a slanted line. This one does have a quote unquote asymptote as well. But notice that in that one, the degree in the top is 3, the degree on the bottom is x. If I were to divide that out, and maybe using long division or synthetic division, you would end up with a quadratic. This actually has a quadratic asymptote. And so you could look at that and you'll see that in the graph itself, the ends are going to follow the two ends of a parabola. So a little bit of information on that. We might come back and talk about that in more detail. All right, let's slide down here to the bottom. So the main idea here is that when the degree of the denominator is smaller than the degree of the numerator, if they're asking you for a horizontal asymptote, you should simply say it doesn't have one. We'll talk in more detail about what if it doesn't have one, what do you do? And then down here for our last pairing that we have, in that one, you'll notice that we're back to having horizontal asymptotes. But what's different about these is that when you're looking at it, the y equals 2, the asymptote's not at y equal to 0 anymore. What do we know about the degree of the numerator and the degree of the denominator? Look here, 2 and 2, the degrees are the same. Over here, the degrees are the same. Now, I used quadratic, but if it was a cubic and a cubic or a fourth power and a fourth power, the key is that the degrees are the same. So when the degree of the denominator and the degree of the numerator are equal, you do have a horizontal asymptote. But you'll notice I had you go ahead down here and take the lead coefficient ratios, and the lead coefficient of the top is 2, the lead coefficient of the bottom is x squared, and when they divide out, they give you 2. Now, and just to be thorough, to show you this idea of the limits for this one, and I'm not going to do both sides, but I'll do the right-hand side. The limit as x goes to infinity of this function h of x. Again, we still survival of the fastest. This is not the only, this is the only technique that we use for end behavior. Other limits, you're going to learn a whole bunch of techniques in calculus next year, but for this end behavior, the Darwin survival of the fittest is what I would use. If I take the ratio of the dominant terms and then I simplify just like we were doing before, we would end up with just simply a constant, 2. So notice that when I ask you, what does the constant 2 do as x goes to infinity? Well, it doesn't change. It stays at the constant of 2. And so this right here gives us the y equals 2 horizontal asymptote that you're looking at. Now, of course, we would never do this much work in pre-calculus. In pre-calculus, we're going to say, hey, it's the ratio of lead coefficients, and we would get that. So down here at the bottom, we just summarized those three things. I like to put when you have a horizontal asymptote first. So you have a horizontal asymptote in exactly 2 cases. When the degree of your denominator is larger, when the degree of your denominator is equal to the degree of your numerator. You do want to know what that horizontal asymptote is. It's either 0 when the degree of the denominator is larger, or the ratio of lead coefficients when the degree of the denominator is equal. And then our degree of the denominator smaller, you have no horizontal asymptote. And I'm going to add f of x has either a slant asymptote, which we will talk about in more detail on the next page, or I call it other asymptote, which might be kind of like parabolic, cubic, etc. We don't spend too much time on the quote unquote other asymptotes other than just understanding that it does control the ends of the graph. All right, so now we're going to look in more detail at these slant asymptotes because those are the ones that are kind of the ones that we're most used to taking a look at. What you're going to do in this next part, and then I'll ask some questions in the ed puzzle. Notice that your graphs, they all have slant asymptotes. So we take a look at them. They have these diagonal lines that are going to be the asymptotes. You're going to use these graphs, answer the questions below. Notice that I'm going to ask you to use synthetic division, a little review from the beginning of polynomials, to divide the numerator by the denominator. Show your work for that. Come up with your remainder as well as your quotient from that divisor. And go ahead and write it in the alternate forms. Like, you know, you would say g of x equals, and write it in not the fraction form, which it currently is it. I like to call it the mixed number form, which is how many times did it go into it? What polynomial was your quotient plus your remainder divided by your divisor in that little mixed number format. So do that and then answer this question here. Based on what you've seen, explain how to find the equation of the slant asymptote if it exists. And we'll come back in and we will discuss those. All right, coming back in, there is a couple of things to talk about with these examples, and they might have been a little challenging depending on what you remembered from your synthetic division lessons that we had earlier. So the one thing that's interesting about these, this one was pretty straightforward. Our equation of the slant asymptote was x plus 4. These were very straightforward for you guys to find. It's just finding the equation of a line, slope, y-intercept. This one was easy. Went ahead and remember that you take your denominator, you set it equal to 0 to get the 0 of the denominator, and then we use that to do synthetic division. But I'm going to remind you that synthetic division requires that when we did synthetic division, maybe I should write this over here on the side. Synthetic division, you can use synthetic if you're dividing by x plus a. So it has to be in that linear form of be dividing by a linear form with a coefficient of 1. And if you were dividing by something like or by mx plus b, but this caused some problems when you were doing the division. I'm going to kind of talk about that in the other two examples. So when we take a look at example 2, the straightforward kind of synthetic division, I did set it equal to 0. I got a possible 0. I went ahead and divided. But what you have to remember in kind of talking about this, that we ask how many times did the like over here, we were asking how many times did x minus 1 go into g of x? What I highlighted in yellow is the whole number of times plus your remainder over your divisor, and that is your fractional part. I like to call this the mixed number in polynomials. And so what we see here, that when we do this synthetic division, kind of the weird thing about this is you have to recognize that you're really dividing by x plus 1. Synthetic division, even though I can use it when it's not a coefficient of 1, it is really just dividing by x plus 1 when I do this. So this part right here, where I have the quotient plus this fractional part, that's when I divided by x plus 1. What we really wanted to divide by was 2x plus 2. So I have to multiply by a half or divide by everything by 2. And then notice that when I divide everything by 2, x over 2 is this 1/2 x, negative 2 over 2 becomes this minus 1, and then that becomes 3 over the 2x plus 2. So it's a little bit weird that you have to add back in that coefficient that is on the denominator when you do synthetic, because synthetic is truly set up only for x plus a when you're doing it. Same thing over here on this one. We set it equal to 0. Our 0 for the denominator is negative 2. I ran synthetic, but that was dividing by the numerator by x plus 2. So I was missing the 3. I put it back in, and we end up here. So the moral of the story is that whatever you get for your quotient of your division from synthetic division, if you had a coefficient there, you have to divide it back in.